and W. If manipulating this bracket notation is confusing, and I suggest you think about it as if it is a dot product. If you want to distribute it over, things like that, as if it is a dot product. That notation, you feel a lot more comfortable with multiplying things out. But I hope now you be able to actually do that in bracket, and even though you think like a dot product. All right, and I guess the very first example I gave you is the matrix way of doing it. So it's a matrix. I use the matrix to define this inner product that is not a dot product. And from there, it was a bit tricky to determine positivity and definiteness. Would you agree? From that example you did 4x4, it requires a little bit of trick to figure out if it satisfies the positivity and definiteness, right? Okay. But another example was given like 0 to 1 and p times q dx. Remember that? That's a polynomial. It's very abstract. It's not column vector space anymore. It's a polynomial vector space, and inner product is given like this. For this one, positivity is not too bad, right? Positivity is p squared. If you integrate the square function, is always a positive. Therefore, that being positive is really easy. All right. So there's this. It's difficult to see what's going on, but that certain property is easy. It's very clear. It's very concrete definition, but proving the positivity is a lot harder. Right? I think it's interesting. All right. So I'm going to tell you about the matrix representation of an inner product that is rising like this. So it's a matrix representation. This is a really fun part. And here's an example. H is x plus y plus z equals 0 sitting inside R3. Of course, you want to look at this H as subspace, but can you just look at H as a vector space? Not subspace of R3. That makes perfect sense. H satisfying, these are a collection of x, y, z, right? Something you're doing in Calc 3. So in itself, this one is going to be a vector space. All right. If you have elements like this, if you add two elements in here, it still satisfies this homogeneous equation, and so on. Right? Now it has its own dot product built in there, right? Okay. So dot product is there. So dot product is also defined within that H. The same old dot product. Okay. But what I'm going to do is that this is essentially the dimension of H is what? Anybody remember the dimension of H? Not 3. Not 1. So only one left is a 2, right? How many free variables are there? 2 free variables are there. That becomes a scalar and so on. All right. This is a one homogeneous. If I have like 2 and in 5 variables, you do the echelon form and you can solve this one. All right. So this one is easy, and I've done it last night. So this is going to be a free variable, and that's going to be a free variable. So hope you understand. The H is actually generated by two vectors. Y is one free variable, and x better be like I think I'm going to stick to what I did, 1 and -1. Does that make sense? X plus y plus 0. If z is a free variable, then is 1, 0, -1. So if you do echelon form, you will get here. This is the very silly echelon form here. This is 2 vector. So I'm going to call that one v1, and then we'll call that one v2. Right? So I'm going to begin to write this. It's interesting calculation. The dot product is the inner product defined on that H. It is just not the entire space. Now I'm looking at this intrinsic way of describing. H has these 2 generators, right? So all the vectors inside is of this shape, a1 v1 plus a2 v2. Is that right? That's the meaning of 2-dimension, and v1 and v2 are linearly independent. Correct? That's a plane sitting inside 3-dimensional space. So dot product is the inner product space. So let's do that as a1 v1 a2 v2 is a one arbitrary vector inside the space, right? Another one will be b1 v1 b2 v2. Is that good? So that's another way. If you dotted two of them, then you're going to always end up in the following form. Who sees the coefficient of v dot v dot v1 dot v1 dot? a1 b1, right? a1 b1. How about v1 dot v2? a1 b2, but because it's commute, a2 b1 as well, right? If it is complex case, then you will just keep it in this order and not mess up with the order. But here we have a1 b2 and what is it? a2 b1. That's the coefficient. And let's say v1 b3 will be a1 b3. You kind of see the pattern a3 b1, right? Just look at the index and you can easily verify I'm not actually doing it, right? There's no 3, right? I made a mistake. Sorry about that. I lost my track in here. That's why this case is easy and good. How about what is the last one? Is it v2? Is it v2? v2, right? v2. What is this one? a2 b2. Is that right? That's all that is. So if you remember what this a1 a2 is, this is the coordinate vector of this v1 v2. v1 already has a coordinate, right? 1 negative 1 0, 1 0 negative 1. But if you look at this as a vector space generated by 2, base element 2, we have a coordinate system with respect to our choice of bases, v1 and v2. The vector you're looking at here is really represented by a1 comma a2, as if it is a two-dimensional vector. And this one as a b1 comma b2, right? It's a different coordinate system put on to this plane H. Okay? So then if you dot it, then this is a formula, right? So let me write that down in here. Whatever the operation we're doing here. What is v1 v1? Do you see the v1 v1? Dotting is pretty easy. You know the dot product, right? Is that 2 times a1 b1? What is dot of v1 v2? I think it's 1. I think it's 1, isn't that? v1 v2. Is that really 1? Yeah, it's 1. So a1 b2, a2 b1 is 1, right? How about v2 v2? That's 2 as well as a2 b2. So if I'm looking at a vector, if you rewrite in terms of a coordinate like this with respect to your bases, the product is like this, done like this quickly. Well, this is a lot easier. Why would you do it like this? But it's an idea to, if you have inner product, whatever is a dot product or not, using these bases, you can always write it in this form. Remember, we got this form out of matrix as well, right? So these numbers, it really came from like this 2, that a1 is 1 1 position, a2 is a 2 2 position. This is a symmetric a1 a2, so that they get 1 and they get 1 in here. So purely playing with a coordinate with respect to this base v1 b2, you know what comes here usually? b1 b2. This coefficient 2, 1 and 2. If you distribute 1 and 1, if you do, we have been doing this matrix multiplication from both sides, right? That exactly capture this shape called quadratic form. All that we have two things multiplied in there. Right? It's a little bit of recognition from this example we've been doing. So if you multiply this out, you will recover exactly. That's easiest way to understand, go from here to there. Right? But it's not easy to discover. It's actually going from here to here. Alright? So that part is difficult. It's given. So this expression is exactly put into this matrix form. Alright. If you have a vector space like this, H, doesn't matter if it's a dot product or not, you choose a basis and you think about dotting it or inner product of this most general element in terms of this base element like that. Therefore, you have a coordinate system. You think about what is the inner product in terms of this coordinate entries. Then there's always this matrix. always matrix that governs this one. So this one actually you see this matrix calculation a lot in physics and modern physics. This is exactly how the relativity matrix is defined like this. So the main idea is like this. If you have a basis v1 through vn, then the first entry, this idea, you can easily see idea, applies to dimension 3, dimension 2. This is a v1, v1. That's 1, 1 position. Here's a 1, 2 position. It goes there, and this is 2, 1 position. They're the same thing because it's a real scalar matrix, right? 2, 2 position. Those number just came from that. This is a bottom line. Of course, sometimes you want to memorize it, not going through all the time like this. Who wants to do that? But you need to understand why it looks like that. Once you pass that, this is a really handy formula. Can you imagine that if you have vector spaces over 5-dimensional space, and you want to write down inner product matrix representing that inner product here, doesn't matter dot product or not, this will just change the v1, v1, inner product bracket, v1, v2, v1, v3, and so on, right? Instead of dot product, you're going to have inner product. Does that make sense? All right, so that's the matrix right there that represent, this is a matrix representation of inner product in general. This depends on your choice of what with respect to a basis. If you choose a different basis, not this one, then things will be different, right? Okay. So I sketch this nice picture in here. This is that curve. I use Mathematica to sketch that x plus y plus z equals 0. All right? If you actually plot those two vectors, they're not like this vectors. I'm going to go right above this space. What is this two vector? What nice relationship this two vector have, you think? In terms of angle, it's orthogonal, right? If you sketch those, they're not orthogonal. Okay? But you can imagine they are orthogonal. There must be an orthogonal vector right on that vector, right? So one of the, I think the bottom one is one vector, 1, negative 1, 0, something like that. And then I found the other one. Do you know how to find the other one? So one, if you choose one thing like that, and how do you find the other one that is not V2, but they're perpendicular to each other? What method? Gram-Schmidt's or orthogonal projection, or whatever that I did at the beginning of the Thursday class, things like that. All right? By doing that, you can find this vector. Once you have this two nice vector on that, you can use this as a coordinate system. So what is a parametric circle equation in xy plane? Unit circle equation. Cosine t sine t, right? So if I'm going to show you that parametric equation of this one in there, make it big enough. You see, I'm using v1. I found that's one vector, and v2 is another orthogonal vector. It works like e1 and e2 in xy plane. All you have to do is that x coordinate, relative x coordinate in that plane gets cosine t, relative sine t, right? If you do that, and it's going to create a nice circle in there. If you want to draw one perfect parabola on this skewed plane, and how are you going to do that? Think about an engineering problem. You have to create that perfect coordinate, right? And you want this orthogonal basis to completely control the geometry of a plane that's disoriented from xy plane, like slanted like this, right? Okay, having that control seems like an important problem in many settings, engineering, other settings, if you want to draw a perfect circle and things like that. All right? But here's the idea. Here's a big picture. The mathematicians always like to put into this big picture. H is some space that's sitting inside three-dimensional space. Think about this is a three-dimensional space sitting inside five-dimensional R5 and things like that. And it has this basis V1 and V2, but it is brought down to the level of R2, which one is A1 and A2. So V1 goes to E1, V2 goes to E2. This is a vector space level. V1 is one of the bases, V2 is another basis, and how vector works arithmetically is exactly AE1 and AE2. Add and subtract and scale them all the same. But now H has one more structure. What is it? Inner product structure, which is dot product actually. So I have V1 dot and V2, right? But how do they translate it down here? It's new, what is it? New inner product that is defined like this. Usually E1 and E2, dot product is 0, right? But E1 and E2 is not dot product here now. Is the inner product. Is given by this bracket. All right? So what is this one? I think that was 1. Remember, we did V1 dot V2. Remember that part? Things like that. So that's what happened. You have a vector space, it has inner product structure, and we just made this basis named different. That is going to be an isomorphism of a vector space, but we carry this natural dot product value to be a new inner product on this R2, which already has a dot product. We ignored it. We define a new product in here. Think about, ignore all the setting, and I give you, all right, V is R2, and I have new inner product given by VW, V transpose AW, where A is given by what matrix? 2, 1, 1, 2. We've been doing this problem a lot, right? What I just did is where it came from, actually. It actually came from that some space above there has a natural dot product structure. It came down from there like that. By looking at this this vector, I know you can check this positivity and definiteness. Is that right? I've introduced the method of checking the positivity and definiteness of the metrics, right? Can you prove that this satisfies positivity and definiteness without doing any calculation in this setting? Under this isomorphism, this inner product represents the dot product, right? Dot product already satisfies positivity and definiteness. So whatever the matrix you obtain from this process, you can generalize to 10-dimensional vector, inside, whatever. And this is always, the matrix always you're going to get is positive and definite and symmetric. Positive, definite, symmetric matrix. That you're going to hear again and again. And next time when you're taking a graduate algebra and things like that. All right? So anytime you have a positive, definite, symmetric matrix, a real coefficient, it defines inner product as well, back and forth. That's the matrix. Okay? Let's look at second example. V being P2R. P2 is back. What is P2R? Polynomial of degree at most 2, right? It has this inner product PQ. What was the standard inner product in here? 0 to 1 PQ dx. What is it considered with the 0 to 1? Is any choice you can make. You can even choose negative infinity to positive infinity. Then this integral doesn't exist, right? You see that? Integral doesn't exist. Polynomial from negative infinity to positive infinity is usually diverges, right? So this one really captures the behavior of the function in between 0 and 1. So that is, you can approach it easily. But ultimately, we're not just looking at this polynomial as a function between 0 and 1. We want to look at it as a function between negative infinity to positive infinity, right? Correct? So what would be the technique that we should introduce in here? How should we put this integral so that we define inner product nicely, whatever that means? Is multiplying this e to the negative x business. Remember this Laplace transform and all that? E to the negative x kills this, because if I go from 0 to infinity, if the negative x squared, that's negative infinity like that. E to the negative x squared is decaying, right? As you go further, this x large, and negative power is reciprocal, so it kills everything. Especially is big enough to kill all the polynomial growth. So that converges all the time. So you can use this trick to take this function as an entirety. And it gets more difficult. Integral world, the practicality of computation gets harder, and you know the Laplace transform and all that gets harder and harder. So we remain in here. So computationally easy, but we're really restricting this polynomial as a function in between 0 and 1. But you can change to -1 to 1, whatever, a closed interval will work. 0, 1 is easy computation. All right? So this is the inner product. Let's look at the matrix. All right? What is the matrix? What is the standard basis in here? When you look at, this is very abstractly defined. Everything is canonically defined in terms of inner product and polynomial. There's no choice of basis. Yet we can define vector space structure. We can define inner product structure, right? In mathematics, it's called canonical, and in other area of the world, it's a coordinate free or something like that. And physicists use that term. It's a coordinate free, setting. But what is the standard basis of a polynomial? 1 and x squared, dimension 3. These are linearly independent vectors. They generate everything. All the polynomial is a times a plus bx and x squared, all that, right? So what is the inner product of a1, a0, a1x, a2x, b0, b1x, b2x, squared and squared, something like that. That's the inner product, right? You're going to do all that, and what I was saying is the bottom line is that that coordinate a0, a1, a2 goes there, and that the other coordinate b1, b2, b3 goes there, and there will be some matrix. Remember how the matrix goes? It was about inner product this time, right? Inner product. God. Docket. What was inner product? First base and first base. Okay? This is the first base, second base. Remember that? Third one, first base, third base, right? You just calculate the inner product between those base members, and it makes a matrix. Everything else is calculated like this. What about here? That was this discussion in here. If you multiply out, and you will have this expression, you can reorganize it into this matrix form. That's the dot product. This inner product is the same. If this inner product bracket is difficult to see how they expand, in your mind, I want you to look at it as if it is a dot product. How would you multiply out dot product? You're going to multiply each of them, distribute all that, right? This one is multiplied to that and that and that. That's how you multiply that to a dot product, right? You can do the same thing with the inner product. Inner product capture that algebraic structure. So by doing that, you can reorganize it into this. So what is this one? Second base and first base, the second row. And second base to second base, second base to the third base, right? And this one here, third base and first base, third base and the second base, and third base to third base, right? Now what is the inner product? You multiply these two functions and integrate. Those are usually, this one turns out is 1/2 and that one is 1/3. You can integrate that. All right, this is the matrix. So the matrix really looks like, let me just copy it down here, 1, 1/2 and 1/3, 1/2 and 1/3 on 1/4, 1/3 and 1/4 and 1/5. All right, and I give you this matrix and I ask you, prove this is positive and definite. There will be some calculation you have to go through, right? But if you know it came from this setting, how do you show that? Well, that is exactly this value right here, right? If it is a pp, then it's going to be obviously integration of a positive function, p squared, so it's a positive all the time. And when it's a 0, only the function is entirely 0 and between 0 and 1, things like that. So positive and positivity and definiteness is immediate from this integral, but once you write a matrix like this, it requires some calculation, right? To see why this one is positive. Interesting interplay between these two things, right? All right. So let me All right, let me give you this quiz right now. What kind of basis? What kind of basis generates matrix? You see, this is the thing, right? If you inner product to itself, what happens if these are orthonormal? 1, 1, 1. If you inner product with each other, what is it? 0, 0, 0, right? So we're saying there are suitable choices of basis such that if you do this matrix and then it becomes identity matrix. Okay? There's a suitable choices of a basis called orthonormal basis, then this matrix becomes an identity matrix. Does that make sense? All right. Why does this orthonormal basis exist? Why does it always exist? Second quiz. Right. Better answer? 2 guys claim that. 2 people shows this procedure. If you think about the procedure and then you probably didn't think about it, that always works. No matter what, that procedure always works. Therefore, orthonormal bases always exist for finite dimension. What is that process? Gram-Schmidt's process. If you think about it, not just he asked me to do it, we'll do it. Think about qualitative. Does it always generate a vector? If you look at it there, only problem is that this thing goes to denominator, right? This thing goes to denominator. If you understood that denominator is never 0, then you believe that that procedure always works. Therefore, you generate n vectors that are all orthonormal to each other, right? Therefore, this orthonormal base always exists. All right. So working too much, but I love.